Welcome to CSC 201, Lesson 4.5, Direct Proof and Counterexample, Part 5, Proof by Cases and the Quotient Remainder Theorem. The Quotient Remainder Theorem says that when an integer n is divided by a divisor d, the result is a quotient q and a remainder r. And note that r must be between 0 and d, right? If r were larger than d, then the quotient would just go up by 1, and we would be able to create a remainder between 0 and d. Stated in terms of multiplication rather than division, any integer n and any divisor d can be rewritten as a multiple of q, d times q, plus r. So let's just look at an example. N equals 22 divided by d equals 4. And we want to find the quotient and the remainder. So this is just a little review of long division, if you remember back that far. So we have 22 divided by 4. And you say, okay, 4 goes into 22 5 times. 5 times 4 is 20. You subtract. The remainder is 2. You subtract 20, you get 2. Because 4 does not go into 2. 2 is too small. It's less than 4. This is our remainder. So I can say that n equals dq plus r, and n is 22. The divisor was 4, the quotient was 5, and the remainder is 2. So 22 equals 4 times 5 plus 2. Definitions of div and mod. Given any integer n and a positive integer d, where we have written n as dq plus r using the quotient remainder theorem, n div d is defined as the quotient part of the division, and n mod d is defined as the remainder. So 38 div 3 and 38 mod 3. So I'm going to write 38 as dq plus r. So 38 divided by the divisor that they gave us of 3. 3 goes into 3 once. 0, bring down the 8. 3 goes into 8 twice. 2 times 3 is 6. Subtract, you get 2. 3 does not go into 2, so I'm done. So 12 is my quotient. 2 is my remainder. I can say 38 equals dq, 3 times 12 plus the remainder 2. So that is true. 38 is 36 plus 2. And q is the answer to the div question, and 2r is the remainder, answer to the mod. Okay, so 38 div 3 is 12, and 38 mod 3 is 2. So why do we, what are these good for? So here's a simple example of arithmetic that involves the quotient remainder theorem. If today is Thursday, what day of the week will it be 400 days from now? Well, we know that every 7 days it would be Thursday again. So we want to know how many full 7-day weeks pass, and then how many are left over. So if I do 400 divided by 7, 7 goes into 40 5 times, and 5 times 7 is 35. Subtract, bring down the 0. 7 goes into 50 7 times. 7 times 7 is 49. Subtract, remainder is 1. All right, so 400 days is 57 weeks and 1 day. So 57 weeks from a Thursday is a Thursday. There have been 57 Thursdays, and then 1 day later, it's Friday. Suppose m is an integer and m mod 11 equals 6. What is 4m mod 11? All right, well, m mod 11 equals 6. I'm going to rewrite that using the quotient remainder theorem. So that tells me, I don't know the quotient, but I know the remainder, right? Mod gives a remainder. 11 is the divisor. So n is the integer. 11 is the divisor d. So I can rewrite this. What this tells me is that m equals the divisor 11. So I'll just write it out first. dq plus r, write it with letters. M is our integer, and it's going to be 11q plus 6, because 11 is the divisor, 6 is the remainder, based on the statement m mod 11 equals 6. So then I'm interested in what is 4m. So 4m would be 4 times 11q plus 6, which is 44q plus 24. Now, we're not just interested in what is 4m. We're interested in what is 4m mod 11. So what is the remainder when you divide by 11? So I need to write this as a multiple of 11 plus a remainder. So I need to write this as 11 times something plus a remainder. So, well, I could do the 4q, because the 11 times 4q would give me my 44q. Now, 11 times what is 24? Nothing, but the closest I can get would be a 22, right? 11 times 2 is 22, but I'd still need 2 more. So I've written this 4m as 11 times an integer plus a remainder. And this remainder, it's smaller than, it's between 0 and 11, so I know I've done it correctly, which means that 4m mod 11 is just that remainder of 2. Dividing integers into even 2k for some k and z, and odd 2k plus 1 for some k and z, is based on the quotient remainder theorem with a divisor of 2. The only possible remainders are 0, in which case you can write it as 2k, and 1, in which case you can write it as 2k plus 1. 2k plus 0 remainder, or 2k plus a remainder of 1. So when you divide by 2, there's only 2 possible remainders, but what if you divide by 3? What are the possible remainders? Well, you could have a remainder of 0. 3 divides in evenly. So for a divisor of 3, the remainders could be 0. You could have 1 left over. You could have 2 left over. But you can't have 3 left over, because if 3 is your remainder and 3 is your divisor, then 3 actually goes into your integer n another time. So you can't have a remainder of 3. And when d equals 4, right, you can have a remainder of 0 because 4 goes in evenly. You could have a remainder of 1 or 2 or 3, but you can't have a remainder of 4, because if you're dividing by 4 and your remainder is 4, then that actually means that your divisor d can go in another whole time, can go into into n another whole time. So you can't have a remainder of 4. And then when d equals 5, your remainders could be 0 or 1 or 2 or 3 or 4, but not 5. And not bigger than 5, right? If d is 5 or bigger, then you could divide 5 into your integer another whole time and have a smaller remainder. So that leads us into proof by cases. While attempting to give a proof of a mathematical statement concerning an element x in some set S, it is sometimes useful to observe that x possesses one of 2 or more properties depending on how x is chosen. So at the beginning of our proof, we often say, suppose x is an element of the integers, and then we argue. But what's hidden in there is a particular but arbitrarily chosen. So suppose x is a particular but arbitrarily chosen element of the integers, and then it may be that x could be even, x could be odd. We don't know because we chose it arbitrarily. So there are 2 cases there. So that's a very common set of cases where, well, x could be even or x could be odd. Let's assume it's even and argue, then assume it's odd and argue. Or it could be that x is 0, x is negative, or x is positive, and we have those 3 cases that we need to argue from. Or if we've chosen 2 elements from the integers or the real numbers, It could be that their product is negative or their product is positive, and each of these would actually have a subcase, right? So if xy is negative, it would have subcase would be x is negative, y is positive, and subcase 2, x positive, y negative. That's how you get a negative product. They have to have different signs. And then for xy positive, we would also have two subcases. If a product is positive, then x and y have to have the same sign. They're either both positive or they're both negative. So we started with two cases, and then each one had two subcases. So sometimes you have to prove, just by exhaustion, go through all the cases. All right, so here's an example of a proof by cases. We want to prove that if n is an integer, then n squared plus 3n plus 5 is an odd integer. Okay, so for any integer n squared plus 3n plus 5 is odd. So we suppose n is an element of the integers. That doesn't give us a lot to work with. Usually we have some kind of definition or something that I can apply to n, argue, and show that n squared plus 3n plus 5 is odd. So what I'm going to do is I'm going to say, well, there are two cases. For an arbitrarily chosen integer, it could be even or it could be odd. So we'll list them. Case 1, n is even. Then n equals 2k for some k in z. Thus, n squared plus 3n plus 5 would be 2k squared plus 3 times 2k plus 5, which is 4k squared plus 6k plus 5, which is 2 times 2k squared plus 3k plus 2 plus 1. Since 2k squared plus 3k plus 2 is an integer, n squared plus 3n plus 5 is odd. So I've proven it for case 1. I've shown that if n is an even integer, then n squared plus 3n plus 5 is odd. But that's only half the integers. My other case is n is odd. And we do a similar argument. N is odd, then n equals 2k plus 1 for some k in z. Thus, n squared plus 3n plus 5 is 2k plus 1 squared plus 3 times 2k plus 1 plus 5. We distribute, we combine like terms, and we get 4k squared plus 4k plus 1 plus 6k plus 3 plus 5. Combine like terms, 4k squared plus 10k plus 9. And then we need to write this as 2 times an integer plus 1. I'm trying to prove that it's odd, so I need to factor out a 2, at least from the first two terms. So I have 2k squared plus 5k. I can't factor out a 2 from the 9, but I can think of 9 as 8 plus 1. And then I would put a 4 here to get the 8, and then I need to add one more. And now I've done it. I've written n squared plus 3n plus 5 as 2 times an integer plus 1. So I just finish this up by saying since 2k squared plus 5k plus 1 is an integer, n squared plus 3n plus 5 is odd. And now I've shown it for both cases, whether n is even or n is odd, n squared plus 3n plus 5 is odd in both cases. All right, I've got one more example for proof by cases, but we just need to introduce this vocabulary word first. The parity of a number refers to whether an integer is even or odd. Its evenness or oddness is its parity. So we want to prove for any two integers of the same parity, 3x plus 5y is even. So same parity means they're both even or they're both odd. So those are our two cases. So any two integers of the same parity. So we would suppose x and y are elements of the integers such that x and y have the same parity. So case 1, x and y are both even. They would have the same parity if they're both even. Okay, then x equals 2k and y equals 2j for some k and j in the integers. Thus, 3x plus 5y is 3 times 2k plus 5 times 2j, which is 6k plus 10j, which is 2 times 3k plus 5j. Since 3k plus 5j is an integer, 3x plus 5y is even. So we proved it for the first case where x and y are both even. So they do have the same parity. They're both even. But there's another case where they have the same parity where they're both odd. X and y are both odd. Then x would be 2k plus 1, and y would be 2j plus 1 for some k and j in the integers. Thus, 3x plus 5y would be 3 times 2k plus 1 plus 5 times 2j plus 1, which is 6k plus 3 plus 10j plus 5, which is 6k plus 10j plus 8, which is 2 times 3k plus 5j plus 4. And since 3k plus 5j plus 4 is an integer, 3x plus 5y is even. So I showed it in both cases. When x and y are both odd, 3x plus 5y is even, and if x and y are both odd, 3x plus 5y is even.